Hi, today I'll talk about BuildIt, which is a type-based multi-stage programming framework for code generation in C++. This work was done at CSAIL, MIT, with my advisor Professor Saman Amarasinghe. First of all, this is quite a loaded title. So I'll break it down into a few main keywords and explain their meaning in detail. The first keyword here is multi-stage programming. In traditional single-stage programming, the developer writes some source code and passes it through a compiler to get an executable. This executable is then executed on certain inputs to produce an output. In multi-stage programming, however, the output of this first stage is again some source code. The developer compiles and executes this with a new set of inputs to produce more source code. This process can be repeated arbitrary many number of times before getting the final output. The next keyword is type-based. In the context of multi-stage programming, this means that BuildIt uses the declared types of variables and expressions to decide which stage they will be evaluated or bound in. Here, I have shown examples of two different types being used to declare variables to be evaluated in two stages. While we are explaining all the keywords, I would also like to add that BuildIt is lightweight. This means we don't need any special compiler or execution environment to use BuildIt staging capabilities. Just like any other library, we can include some headers while writing the program and compile the code with the standard C++ compiler to get multistaging. With the title explained and out of the way, let us answer the most important question. Why use multistaging? The simple answer is that multistaging is everywhere. You might have seen dynamic websites where server-side languages like PHP execute on the server to produce HTML that is executed on your browser. You might have also seen libraries like TensorFlow where the code that you write produces an execution graph that is compiled down before executing on the actual inputs. You might have also seen or used domain-specific languages like Taco, Halide, or Graphite. The developer writes the source code in these languages, which is then converted by a special compiler into low-level C++ and CUDA to be executed on CPUs and GPUs. Finally, many of us have used metaprogramming through C++ templates or in our favorite languages like Haskell, OCaml, or Scala. These are all examples of multi-stage programming or metaprogramming or generative programming. I will be using these terms interchangeably in this presentation. Some of you might ask, what is the technical reason behind using multi-stage programming? Software development is a process of striking a balance between generality and specialization. Writing generalized software lets us support many applications with little to no extra effort, which makes development easier and faster. Writing specialized implementation tailored to specific scenarios and inputs, on the other hand, gives us the best performance. Let us look at this very simple example. Here on the left, I have a generalized implementation of the power function that calculates base power exponent using repeated squaring. This function can be invoked with any inputs. On the right, I have a specialized implementation that calculates base power 5 and another specialization that calculates 5 power exponent. These specialized implementations are easier to recognize, will have better branch prediction during execution, and will benefit from all the compiler optimizations. But with multi-staging, we can write a generalized implementation once, pass it through our favorite staging framework with certain inputs to generate a specialized implementation, giving us best of both the worlds. This reduces the development time and effort without compromising performance. Another related question you might ask is why do multi-stage programming in C++? Well, first of all, C++ is the language of choice for implementation of most of the high-performance DSLs that we saw before. Domain experts like physicists and mathematicians are also familiar with writing and optimizing C++. C++ is in fact the de facto high-performance language of the software development world. Secondly, the existing metaprogramming facilities in C++, that is templates, are hard to write and even more hard to debug, especially for beginners. C++ also has some unique challenges in that it doesn't have support for introspection and dynamic types, which makes this problem of studying multistage programming for C++ even more interesting. Now that I have convinced you that we need multistage programming, you might ask, how do I start writing multistage programs? There are many ways to implement staging, the simplest being text-based staging, where the first stage program outputs as string the program for the second stage. This is seen in server-side languages like PHP that produce HTML. The obvious benefit of such an approach is that it doesn't require any specialized compiler. But the drawback of such an approach is that we don't have early type checking or toolchain support like syntax highlighting or autocomplete because the second stage program is simply treated as strings in the first stage. In contrast, the other approach is to build staging support in the language itself. This is seen with C++ templates or DSLs that we have seen before. This approach can get us early type checking and toolchain support, but we have to build specialized compilers for this approach. The most promising approach is to use operator overloading to embed a language in the existing language. This is seen in Python libraries like TensorFlow, where all the operators are overloaded to produce a program tree that is then compiled and executed. This approach doesn't require any special compiler, has support for type checking, syntax highlighting, and autocomplete because we are simply writing Python with a special library. Well, does that mean the problem is solved and we can move on? Well, let's look at the last approach in detail. Languages like C++ do not have reflection and cannot overload control flow operators like if then else and loops. In this case, with operator overloading, we can extract the individual expressions, but there is no way to put them together into a conditional or a loop. The developers then have to resort to specialized constructs like tf.conditional or tf.while to implement control flow. Well, that doesn't seem like too much of a problem. We would have to learn a few more functions and their syntax. Let us look at this example where we stage the previously seen power function with two different specializations. First, we have an implementation where the base is evaluated in stage 1 and the exponent is evaluated in stage 2. Since the exponent is evaluated in stage 2, we have to use the special tf.conditional and tf.while constructs. On the right, I have a specialization of the same power function where the base is to be evaluated in stage 2 and the exponent is to be evaluated in stage 1. In this case, since the exponent is a normal Python integer, all the code that deals with it needs to be rewritten to change the specialization. This certainly increases the amount of effort and time the developer has to put in. That brings us to BuildIt, which is lightweight, so it works just like a library and doesn't require a specialized compiler, provides early type checking and toolchain support, and most importantly, allows us to move between two stages very easily. If that seems exciting, let us see how one would write multi-stage programs with BuildIt. Here I have an excerpt from the BuildIt programming manual, which says that we start by including the BuildIt headers. Then there are these two new templated types that we have to learn about. And the rest of the stuff is the same as plain old C++. What this means is that we use the same syntax for all the stages and don't require any specialized constructs like tf.conditional or tf.while. Let us now look at these types in detail. The dynamic type is used to declare variables and expressions that are to be evaluated in the second stage. Any expression written using these types will produce the same expression in the second stage source code. This also applies to control flow constructs like if then else and loops. The second type, static T, is used to declare variables and expressions that are evaluated in the first stage. These expressions are completely evaluated in the first stage and simply appear as constants in the second stage. All the control flow based on these types are also completely evaluated to just produce the code from the dynamic T expressions. Let us now see how one would write the power function specialization with this. On the left, I have the specialization where the base is evaluated in the second stage and is declared as dynamic int. The exponent is evaluated in the first stage and is declared as static int. Now, when I change the specialization, all I have to do is to change the declaration of these variables. The rest of the code remains exactly the same, thus reducing all the effort required. This was for two stages. What do we do if we have more than two stages? Do we have to add a new type for each stage? No. The dynamic T type can be arbitrarily nested. Here, dynamic of int produces dynamic of int, which produces dynamic of int, and so on. Similarly, the static int can also be nested inside dynamic to produce static int. We don't need to nest static T multiple times. Now that we have seen how to write these programs, let us see how BuildIt works and specifically how it extracts the code for the second stage. The simplest case is for extracting straight line code. We have a simple example of a straight line code with two dynamic int variable declarations and an expression based on these variables. First, the constructor of these types are overloaded to produce an AST with the declaration. We will add this to the generated code. The same step happens for the other variable. Now, when the execution reaches the second statement, the star is evaluated first based on operator precedence. This is again overloaded to produce an AST as shown. All the operators are similarly overloaded to construct the AST step by step and finally add the statement to the generated code. This gives us the second stage code for a simple straight line program. After the straight line code, let us look at conditionals. Again, on the left, I have a simple straight line code with a variable declaration and a simple condition based on the dynamic T variable. The first statement is executed in the similar way as before to produce a declaration statement in the generated code. Next, when the execution reaches the if condition, first the expression inside is executed to produce the AST for the expression. This expression then calls the cast to bool operator, which is overloaded in the BuildIt library. This operator now has to return either true or false. But since the dynamic T variables don't have any concrete values in the first stage, it is not able to decide whether the expression evaluates to true or false. BuildIt thus just returns true, but puts a marker here to remember that it had returned true. A similar marker is also put in the generated code. The execution then continues as before to give us the straight line code. But we are not done yet. We haven't explored the else branch. We put aside the code that we have so far extracted and restart the execution. This time, when the execution reaches the condition, the cast to bool operator is invoked. BuildIt remembers that it had returned true before, so it returns false this time. The execution continues to produce the code for the false branch. Finally, we have these two straight line codes generated from the two execution. BuildIt then combines these two to produce an if then else and an AST like this based on the markers it had left. This approach works but has a small problem. Let us look at this simple program with a conditional followed by another statement. If we repeat the process we have seen so far, we get the following program. We can see that the statement appears to be duplicated on both sides of the condition. This leads to an exponential blow up in the size of the code generated, especially if there are conditions following each other. We need to identify these statements uniquely so that they can be merged. This is where we introduce static tags. When extracting the program, we take the program counters and the state of all the static live variables in the program and combine them to produce a static tag. This static tag is attached to the produce statement. It is easy to see why this static tag uniquely identifies each statement in the generated code. Let us now add the static tags to the AST we had seen before. BuildIt immediately realizes that these two statements have the same static tags and erases one of the duplicates to produce an AST like this. This technique avoids exponential blow-up in the size of the generated code. BuildIt also applies memoization and early merging to avoid generating duplicates in the first place. This helps BuildIt in reducing the extraction complexity from exponential to polynomial. Finally, we will see how to deal with loops. Let us first see what happens if we treat the loops just like conditions. When the execution reaches the start of the loop, it will produce an if and start exploring the true branch. The execution will reach the start of the loop again to repeat the process. This will lead to an infinite loop which will produce a malformed program. Once again, we use static tags to solve this problem. We annotate every statement with these tags as we execute the program. When the execution reaches the start of the loop again, BuildIt sees that it had seen the same tag before. It concludes that the generated program will be exactly the same as before and terminates the execution. It then inserts a back edge in the generated program. This gives us the most primitive if then else and go to loop, which has the same behavior as the while loop. After extracting the function in AST, we pass it through a series of post-processing passes to massage it into more readable code, which finally goes through a C++ code generator to produce code to be executed in the next stage. BuildIt also has a user-defined pass infrastructure where the developer can write their own passes and insert them anywhere in the pipeline. More details about each of these and the techniques and the optimizations we apply are in the paper. We also have a few case studies where we applied BuildIt staging capabilities to generate specialized code. In this talk, I want to talk about an ongoing work where we are using BuildIt. We looked at the GraphIt DSL before, which is a domain-specific language for graph applications. Our recent work in CGO 21 added G2, the GPU extensions to GraphIt that enables it to generate high-performance CUDA code to be run on GPUs. The way GraphIt works is that the user writes the program in an algorithm language which specifies what to compute, and also writes a schedule in the scheduling language which specifies how to compute. These inputs are then fed into a specialized compiler that produces the final CUDA code. This compiler is able to generate up to 576 different variations of the same program based on the scheduling language tailored to graph inputs and algorithm features. Our ongoing work simplifies this framework. We replace the algorithm language input with inputs of type dynamic T and the scheduling language input with inputs of type static T. We also replace the compiler with a general purpose graph library written on top of BuildIt. With BuildIt staging capabilities, we are then able to generate high-performance CUDA code to run directly on GPUs. We enabled a special pass in BuildIt that automatically converts nested loops into CUDA kernels based on user annotations. We also added support for modular types where the developer can stack capabilities like Lego blocks to perform analysis like data flow and dependence analysis for more specialized code generation. Finally, we added support for pattern matching where certain nodes in the generated code can be fused into specialized implementations as required. With all these techniques combined, we plan to support generating all the 576 variants with far fewer lines of code than the GraphIt compiler. With this, I would like to conclude my talk. I would like to mention that the BuildIt framework is available open source at the following URL. You can also try BuildIt online without having to download and install it. If you have any applications that can benefit from staging, or if you're simply interested in learning more about BuildIt, please contact us. Thank you.